0 critical point. It's not. Fine. So find, let's say, xx of pi 0. Let's find fxy of pi 0. Let's find fyy of pi 0. Let's find fx of pi 0. Let's find fy of pi 0. Let's find all the values of the function and its derivatives out to second order from what we're given. All right, let me answer part A to start with. The answer is, why is 200 a critical number? The answer is simply, we have the power series expansion. There are no linear terms. It jumps straight to quadratic. So this tells me that, like, the gradient of f at the point 2, 0, 0 is equal to this. So therefore, it's a critical point. Right? And so this is really the only kind of trivariate question I can reasonably ask you. I have to ask you a question, if I do ask you a question like this, where you either have all of them are negative or all of them are positive, like the quadratic terms, and there can't be any missing. It's got to be everything. But if it's everything there, either positive or negative, then just common sense answers the question. So the formula for f of x, y, z is 10 minus the sum of squares. What happens as you get a little bit away from the critical point? You got 10 and you're taking away stuff, right? So that means that 10 is a local maximum. Anywhere close to it, you're taking away from 10, you're smaller. So it's a local max. Right. Now, for functions of two variables, we had that second derivative test. So there we could deal with, like the mixed terms. We calculate the Hessian. We have the second derivative test. You should make sure you know the second derivative test clearly and carefully, right? Okay, so this one, we can just read it off. That's 10. The coefficient of that is 3. The coefficient of y is, 1. Now, here's where it gets a little bit trickier. Over here, we need to remember what the multivariate Taylor expansion looks like there. It's like 1/2 fxx times x minus pi squared, and then it's plus fxy of x minus pi times y, and then 1/2 fyy times y squared in this context. And I'm suppressing the point dependence, but that's the quadratic term in the multivariate Taylor expansion. And so if we compare that to what's given, you can see that we have to have a 2 for this one, and we have to have a minus 2 for the y derivative. But the xy derivative apparently is 1. So there's this kind of problem. Of course, I think the algebra, the algebraic trouble of the Lagrange multiplier problem is essentially the same algebraic trouble of the critical point calculation. Here's a function of several variables. Find the critical points. Like, what kind of algebra do you face there? Multivariate polynomial algebra. And so the key thing for solving those is to remember just basic principles that if you've got a product of things is 0, it must be that one of the things in the product is 0. And that is what should guide you. That and the idea that the Lagrange multiplier has to be non-zero, that's helpful. But I would say you guys some of you were a little bit weak on like finding critical points. I don't believe for you guys that that's probably because you're weak in algebra. It's probably because you're not confident enough that you can do the algebra, maybe. I think that's probably more likely the situation. So you just have to, pick a path and like chase scenarios to work those kinds of problems. But one last problem here, and then we'll be done for today. Example 8. suppose we've got the snow cone. And let's suppose that this is like phi equal to pi over 3. And this is like rho equals to 10. Let's calculate the flux through the snow cone of the vector field f of x, y, z equal to, let's do x, y, z. That should suffice. Maybe that's too easy. We don't have a lot of time though, I guess. I'd like to calculate it both directly and by the divergence theorem though, okay? So directly, what's that calculation look like? So find, the flux of this vector field two ways. One directly from definition / notes, and the other way is by the divergence theorem. So the direct way, well, first of all, let's be smart about this. This is the vector field 1 over the square root of x squared plus y squared plus z squared. Oh, my bad. Well, this is awkward. I'm right this way. Okay. My point to you is that this is rho hat. So that's a nice formula for it if we take that approach. So we have two things. We have the flux over the top of rho, well, let me just say f ds. I'll just write it symbolically, plus the integral over the cone part of f ds. Now you guys help me out. The top, we're doing the integral from 0 to 2 pi, the integral from 0 to pi over 3 of what we got. We've got 10 rho hat dot product with 10 sine phi d phi d theta rho hat. Where did that come from? Something you should definitely have on your formula sheet is that, like up here, you've got ds vector is r squared sine phi, right? D phi d theta rho hat. And I would encourage you to know what rho hat actually means in terms of the Cartesian coordinates, right? It's like cosine theta sine phi, sine theta sine phi, cosine phi, right? If you don't know that kind of thing and you need to know it on the final, just ask me, right? Just ask me. I'll probably help you. Now this one I don't remember. You guys are gonna have to help me out. What's the ds for a cone? If I want it to be pointing in like, I mean, I know it's in the phi hat direction. Can you guys help me out? What is it? It's.
You don't need to calculate it because it's final to.
Well, that's true, but I just wanted to, is it rho? It's rho sine phi, is it?
That's right.
And you got yourself a d phi. No d phi. Phi is constant, so there's no d phi. So like d rho, d theta, and like you just told me, phi hat. Now Sam is right. It's irrelevant because this piece gives you 0. I'll write it out symbolically though because it's useful. So 0 let's as an exercise on how the bounds go, it's useful to us. So we go from 0 to 10, 0 to 2 pi, and we've got our 10 rho hat vector field, except it's not 10 rho hat now, it's what? It's rho hat here, because rho is not fixed at 10, rho is a variable on the cone, dotted with my rho sine phi d theta d rho. But, and then there's a phi hat in here somewhere. And Sam is actually right. Of course, the phi hat dot rho hat is 0. So that piece is 0. Uh-oh. And this piece is giving us 100 times 2 pi times minus cosine of phi evaluated from 0 to pi over 3, also known as 200 pi times whale minus 1/2 plus 1. So I guess we've got 100 pi. That's kind of nice. Is that right? Now, on the other hand, the divergence theorem way to do this is what? It's a lot easier, isn't it? We just have to calculate the triple integral over the cone, snow cone, right? The whole deal of the divergence. What's the divergence of this vector field? It is 3 dv. So we've just got 3 times the integral. How do we get the volume of the cone? We got 0 to 10 for rho, 0 to 2 pi for theta, 0 to pi over 3 for phi, and be careful, we've got rho squared sine phi. Some of you guys were, and you know better. Some of you know better. You definitely know better. I've noticed this. A couple of you guys are changing dv to just the product of the differentials of the variables, but you're not including the Jacobian factor. Don't do that. Remember, if we're using, like if we're setting up an integral in terms of non-Cartesian coordinates, we have to include the Jacobian factor like I just did here. And let me be optimistic and say that that equals 100 pi. So anyway, but yeah. Anyway, it's been a fun semester, guys. You guys are all aware that I posted did I post 2 old finals? Yeah. So if you have questions about that, you can email me or come see me, whatever. I don't have many office hours really during final exam period, but I could plan to be here like Friday afternoon, like from 1, if that's helpful, but you'd have to ask me to do it, otherwise I won't. And similarly, like in the middle of Monday, I might be around, but I think your test is done by then, so it's kind of irrelevant. Anyway, see you guys.